Welcome back, everyone. We are going to continue our discussion from the previous class, in which we are going to extend the concept of shape function to shape vector and employ it for discrete structures. Okay, and then see how to get the response. Okay, so in today's class, we are going to continue our discussion on generalized SDOF system. Okay, and just to recap, basically what we said, a generalized STO system is a continuous system. Okay, so let us take an example of a simply supported beam here, which can be transferred to a single degree of freedom system. Okay, so let us consider the spring mass representation. Okay, with K equivalent and M equivalent. And if there is a force that is being applied, either a point load or it could be any general force. Okay, let us say it is represented as kpxt. So again, I can write this as p equivalent. Okay, so basically what we said, a continuous system can be transferred to a single degree of freedom system using something that we said shape function. And shape function is nothing but an assumed deflected shape of the continuous system. Okay, and typically in this procedure, we consider any approximate function that can represent its deflected shape. So when I say deflected shape, it can be any shape that represents the deflection under the applied load. Okay, and then basically we derived the equation of motion and also the expressions for the K equivalent, N equivalent, and P equivalent, utilizing the mass and the stiffness distribution as well as the assumed shape function. Okay, and we said that this method is approximate. Okay, and the accuracy of this method depends on the accuracy of the shape function that we are considering. Okay, so the expression that we derived for M equivalent was, let me just write down. Okay, M of x times phi of x square times dx and integrated over the whole length of the element, the structural element. Similarly, K equivalent expression we derived as EIX, which is the flexure rigidity, times double differentiation of the shape function, this square, integrated over again the whole length. Okay, and then we also define the expression for L equivalent, which is nothing but 0 to L mx phi x times dx. Okay, and basically using these equivalent parameters, okay, the equation of motion that I had derived was M equivalent times z double dot t, the acceleration in terms of generalized coordinate z. If you remember, the total deformation we had written as phi x times zt, where phi x represents the deflected shape or the shape function, and zt is basically the time variation, okay, which we called as generalized coordinate. So we got this. Okay, so if I wanted, I could include the damping term as well, but remember, as I said, damping term, typically we do not have an expression for the damping term because damping we get from experiments. So we get the damping ratio and we convert it to get actually the C equivalent. Okay, so let us write down without damping here. Okay, the expressions that we had was K equivalent times zt, and that was equal to L equivalent times ug double dot t. Now this was the expression that we had derived for ground excitation, okay, or earthquake excitation, in which basically the ug double dot was the acceleration of the ground. Now I can divide the whole thing by M equivalent, and I can write this expression as zt times omega n square zt equal to minus L equivalent times M equivalent Ug double dot t. And this term I can write down another factor which is gamma equivalent. Okay, so that my expression or the equation of motion, I can write it as this. Okay. And now this one was for undamped system. Okay, for a damped system, we get the zeta value from experiment, and then I can utilize the same expressions that we had previously used for single degree of freedom system. Okay, and write down this expression here. Okay, and this is for damped system. Okay, so up to this point we had derived our equation of motion. Okay, and basically our frequency omega n square is nothing but k equivalent by m equivalent, which I can substitute the expressions and I can find out the values. Okay, so I can write this as EIX times pi x integrated over 0 to L, and then I have the expression for m equivalent, which is mx times pi x square dx. Okay, so this makes our job a lot more easier. This allows us to analyze a continuous system without having to approximate it as a multi-degree of freedom system. Okay, so a continuous system can be reduced to a single degree of freedom system, which we call generalized SDF system, with the help of a shape function. Okay, all right. Now, the natural sequence of things once we get the equation of motion is to find out z of t. Okay, after we have obtained z of t, the question comes for this. Remember, for a single degree of freedom system that we had considered, okay, discrete system, okay, only one degree of freedom, so there was no x term here. So wherever the degree of freedom was defined, there we had defined our total deformations. What I'm saying, if we had considered this system, okay, in this case, okay, whatever the u value for this was actually, okay, at this location only. Now for a continuous system, I know that u would be different at different location. So this also, okay, poses the question, what happens to the forces at different location? So I know that my u is now a function of x and t. Okay, so I would also have a different point. What are the internal forces and moments? Okay, so internal force and moment. Let I call internal forces and moments. And to do that, again, we are going to utilize the same method that we have done. So we are going to utilize something called equivalent static method, in which, okay, so to get the internal forces, okay, so to get internal forces, all right, now this method basically allows us to find out to obtain the internal forces. So in this method, what do we do actually? Let us consider, okay, that we have a beam and then there is a distributed load. I don't know what is the variation of that. Now if you might remember from your solid mechanics course, okay, that if you have a distributed system like that with only flexure rigidity EIX, then I can write down my omega x, which is the applied load, is equal to EIX times U double dash x times, okay, so the differentiation of the whole expression. So this is the applied force. Now equivalent static method basically says that if I have analyzed a system and I found out what is the value uxt, okay, or let us say at any time instance I found out what is the ux, the internal forces in the system can be found out by applying an external force, okay, which is equal to omega x here, okay, and the same displacement ux through the stiffness component of the structure. Okay, so what it is saying, and I can say I'm only considering the stiffness component, it means I'm doing a static analysis. So there is no mass here. So equivalent to static analysis there, you do the dynamic analysis, you find out the deformation at each and every point, or each and every time instance. Once you find out, then at any particular time instance, you apply an external force and do the static analysis of the system, okay, to get the internal forces. And this external force is nothing but it would be as a function of the stiffness component times the dynamic deformation, okay, which in this case basically this external force is this here. Okay, now what I'm saying, this omega x, so you might have used the notation omega s, I'm just going to say this is my fx. So I'm going to apply this force, external distributed force, to my beam, and then I'm going to find out, subject to this force, what are the internal forces using static analysis. Now no need to do any dynamic analysis. Okay, so I can do that. I can substitute the value of ux equal to phi x times xt. Okay, so that I can write my f os, let us say it is at any time instant, so that I would write it as e ix times phi double dash, okay, down again, okay, and I can take zt outside. Okay, so this is the expression that I would be using to get the external force. So this is the external force that need to be applied. Okay, now we can do some simple manipulation and we can see that the same expression can be converted to, okay, same expression can be converted to omega n square m of x times phi x times zt. Okay, and it is more often this is like, this is the expression that we would be using to get the external static or the equivalent static force to which the internal forces can be obtained at any time instance. Okay, and the derivation from how to get from here to here can be found out, okay, anywhere. Remember, to get this we are just going to utilize this expression that we have here and then also use the principle of virtual work, such that the work done by the external force st times del, okay, so I'm going to write down this times del ux times dx over the whole length. It should be equal to work done by the internal forces, which is due to the flexure, or let us say the moment here. Okay, this is moment times curvature times dx. Okay, and we can substitute and utilize this expression, and we will get finally this expression here for equivalent static force. Okay, once the equivalent static force is known, other part are simple. I can just apply this equivalent static force and get the internal forces. Now, more often than not, as we have previously discussed in earthquake analysis, okay, so remember this is the response that we are considering for ground vibration, okay, or earthquake analysis. Okay, so for earthquake analysis, usually peak response is of most important, one of the most important parameter. Okay, so we consider mostly peak response, and we know that peak response of any single degree of freedom system can be obtained using response spectra, okay, or design spectra, depending upon what you have been provided or given. So let us say this is the response spectra, so that let us call this as pseudo acceleration and this as g. Similarly, I would have displacement, okay, which would, let us say, look like something like this. Okay, not G, sorry. This is A as units of G, this is versus time period, and this is D versus time period. Okay, so remember, these response spectra are basically response of any system, okay, of this type. So if I write it, okay, remember these were drawn for, let us say, Z double dot 2 zeta omega n Z dot plus omega n square Z, and this is equal to minus UG of t. So this is response spectra is basically correspond to this equation here. Okay, and same for the deformation. But remember, the equation that we have for generalized Fourier system, left hand side is same. However, in the right hand side, I have a factor which is gamma equivalent. Okay, now since we are considering linear system, if I know the peak response of this system, to get the peak response of this system, I just need to multiply this with the factor gamma equivalent. Okay, because my ground motion is now multiplied with this, so the response would again be multiplied with this factor. So the peak response would be multiplied with gamma equivalent. So for this case, the peak generalized displacement can be written as Z naught equal to gamma equivalent times D, where D is the peak deformation. Okay, which can be further written as, if you write the D as the pseudo acceleration divided by omega n square, so this can be written as A divided by omega n square. Okay, now remember, once we have obtained the peak response, then I can get the peak value of the displacement as uxt. Okay, so you want to get the maximum of this one over time, of course. Okay, so this would be ux. Okay, again the peak displacement would be function of x, because the peak displacement would be different at different location in the structural element. Okay, so this can be written as u naught x equal to gamma equivalent times d times phi x. Okay, basically all I'm doing is writing down this one as phi x, or instead of doing that, let me just do this. This would be equal to phi x times z naught. And what is z naught here? Gamma equivalent times d. So that I can write this as phi x, okay, times d. Okay, so peak equivalent static force can be written as, okay, remember, this is my unit. So peak equivalent static force, if you look at the expression here, all I need to do is substitute zt equal to z naught, and that would give me the peak value of the equivalent static force. So let us write down that as mx phi x times z naught, which can be written as gamma equivalent times mx times phi x times a. Okay, because if you write z naught equal to this expression here, then omega n square cancels off, and you get basically this expression that you have right here. Okay, so subject to this, we can find out the internal forces and the moment. And let us see how do we do that. So we are going to take the example of the cantilever. Okay, the cantilever column that we had considered. And in this case, basically we had said that, okay, the inertial forces would look something like this, Fi as a function of x and t. Okay, we had also said that, okay, for this case, let us apply. We want to find out the response of the system subject to this. This is the equivalent static force. This is 0 at x equal to 0, because phi x equal to 0. Okay. Now, if I want to say find out what is my shear at any height y, okay, then let us see how do we do that. Or instead of saying at y, let us say I want to find out shear at any height x. So to do that, what will happen? The shear at this point would be due to contribution of all the forces which are above this one. So, or the sum of all equivalent static forces which is above this one, and this just comes from the free body diagram. So, shear at any point which is at height x, let us say this is Vx that I want to find out, would be due to all the forces which is basically F naught x above that location. So, to do that, let us do one thing. Let us consider any small element which is at height of y, okay, and of differential height dy. So this is not fx now. Let us say this is f naught y. Okay, so Vx basically is integration from, okay, x. Okay, first let us write down the expression sum of all the forces. So it would be f naught y, all right, and dy integrated over x to the total height. Let us say it is L or H or whatever you are considering. So this gives you the shear at any height, location, or whatever you want to say at distance x. Okay. Similarly, the moment at this point. Okay. So let us say this is the direction. This is the direction we are considering. Correct? Yeah. So the moment, let us say it is something like this. Okay, or it would be an opposite direction here. Okay, so mx again becomes similar. Okay, so I'm going to utilize the same expression here, x to L. This would be moment of this force F dy, and the lever arm would become y minus x. So let me rearrange this expression. This becomes y minus x times F naught y dy integrated from x to L. Okay, so these two expressions we utilize to get the basically forces and or the shear forces and moment at any height x. Okay, now the parameters that are of more importance in this case are the base shear and the base moment, which are typically used to find out what is the base shear of a structure in equivalent static method. Okay, so in that case, what I can do, okay, I can write down at the base VB, all I need to do, the lower limit is basically now becomes 0, and this is F naught, okay, y and dy integrated over the whole height. Okay, and you would see that I can write this expression, okay, in terms of, if you substitute the expression for, let us say, F naught y, which is right here. Okay, I can take, or let me first write down like this, omega n square, or let me use the second expression here. So it is this times mx pi x, or the integration variable here is y. It doesn't matter really in this case. Okay, this need to be integrated. Now this is constant, not a function of actually. So I can write this as my pi y dy. Okay. Now if you remember, this expression is nothing but L equivalent. So I would write this expression as L equivalent times gamma equivalent times A. Okay, this is the expression for the base shear. Okay, similarly, base moment I can also write down MBO is equal to 0 to L. Okay, in this case, y times F naught y dy. And again, when I substitute this, I would get this as Okay, some L equivalent dash A, where L equivalent dash is actually 0 to L y m y I y ty, or you can write in terms of x. It doesn't actually matter. So these expressions can be utilized to find out the base shear and base moment for any continuous system. Okay, now remember that till now we have considered basically the ground shaking, and we have derived the equation of motion for ground shaking. However, instead of the ground shaking, if you have the external applied force which may be distributed or concentrated, but let us say in general we write the external applied forces, okay, as distributed force P of x of t, okay, instead of the ground motion UG double dot t. So in that case, the same expression I can derive, okay. Only thing is that I would have a P equivalent t terms, which is nothing but in this case pxt times phi x times dx integrated over the whole length. Okay, and that you can just find out. So in this case, my P equivalent becomes whatever the force distribution that is given to you. Okay, multiply with the shape function phi x and integrate over the whole length. All right. So this is instead of ground excitation, if you have a force acting throughout the length of the structural element, then we can utilize this expression to find out and then further solve the system. Okay. All right. If this is clear, then let us do an example, because that would make this discussion, like, put it in perspective. Okay. So what do we actually have here? Okay, let us consider this. Okay. We are going to consider the same problem of a cantilever, basically column here. So let us do this example here. Okay. So what we have again, a cantilever column, which basically representing a chimney, which is fixed at the bottom. The total height is 200 meters. Okay. And this is of hollow cylindrical shape of total or the external diameter equal to 16 meter. The internal diameter, or instead of internal diameter, the thickness of the wall is given as 1 meter. Okay, let me draw it in a larger view. So this whole diameter, okay, this whole diameter is actually 16 meter. However, this thickness is 1 meters, 1 meter. So in that case, the internal diameter would become actually 14 meters. All right. Now, additional information is given that for this case, it is of concrete material of density that you can assume as 2400 kg per meter cube. The modulus, elastic modulus, can be taken as 25,000 MPa. Okay. The damping can be assumed as 5%. Okay. And it is given that the expression for SA by G, or the spectral acceleration, can be taken as 1.8 divided by the natural time period. Okay, so I mean, this is for any design spectra, in which case, okay, this expression can be given or can be taken to find out the spectral acceleration for this problem. Okay, so let us now solve the problem. See, in this type of problem, the first step is always to determine what is the basically the section parameter and what is the modulus of rigidity, the flexure rigidity on all those things, so that we can find out the solution. And then assume the shape function. Now for this case, you can assume the shape function to be 1 minus cos pi x by 2l. And if you remember from the last class, if you assume this to be the shape function, okay, the expression for the frequency was coming out to be 3.66 divided by the total length, okay, times EI divided by the mass per unit length. Okay, so at this point of time, pause it and then take 10-15 minutes to solve this problem. Okay, all right, let us discuss this problem. Okay, so let us go step by step. The total length is given as 200 meters. Okay, now remember, we need to find out what is the mass per unit length. So we need to find out what is the mass per unit length. We also need to find out the inertia. So these two parameters need to be found out to determine the value of omega n, so that I can find out Tn, because once I get the Tn, then I can find out what is the spectral acceleration. Okay, so let us do that. Let us find out mass per unit length would be nothing but whatever the density of the concrete times the area, not the volume. If I consider area, multiply it with the density of the concrete, it would give me mass per unit length. Now in this case, density is 2400 kg per meter cube, and the area would become pi by 4 times 16 square minus 14 square. Okay, and this gives me basically the mass per unit length as 113, okay, times 100 kg per meter. All right, now moment of inertia of a hollow cylinder, okay, is basically pi by 64 d2 to the power 4 and d1 to the power 4. Okay, so it would be pi by 64 times 16 to the power 4 minus 14 to the power 4. And this you can find out comes out to be 1331 meter 4. Okay, so the flexure rigidity, which is EI, can be found out as 25,000 MPa, and I can convert MPa to Newton per meter square as 10 to the power 6 Newton per meter square times 1331 meter 4. Okay, or let us first omit this, and this comes out to be approximately as 3.33 times 10 to the power 11 Newton per meter square, Newton meter square. Okay, so let us now find out what is omega n, which is 3.66 times L square EI by, okay, EI by m. So I can substitute all these values and I can get the value of omega n is 1.57 radian per second. So the time period can be easily determined as 2 pi by omega n, which comes out to be as 4 seconds. Okay, now I know that for 4 seconds, my pseudo acceleration is 1.8 divided by 4. Okay, and what is also given in this problem, that we need to find out the response of the system of a response spectra, for which this is the spectral acceleration, but scaled to a PGA of 0.05. So in that case, I need to multiply this with 0.05, and this times g would be my acceleration. Okay, and if I substitute that, then I get this as 0.112 times g. Okay, now I know that my displacement is nothing but pseudo acceleration divided by omega n square. Okay, and if I substitute that, I get this as 44.5 centimeter. Okay, so that Z naught would be equal to gamma equivalent times D. So I also need to find out gamma equivalent here, which is L equivalent times M equivalent. And if you remember from the previous classes, okay, I can get either directly by integrating, let us say L equivalent as um, whatever the mass times pi x times dx and M equivalent. Okay, and you can substitute all those values and we can see that you will get this one as approximately equal to 1.6. So that your Z naught becomes 1.6 times D, which is 44.6 centimeter. And this one comes out to be approximately at 71.5 centimeters. Okay, and the peak displacement now. So this is the general peak value of the generalized coordinate. Okay, so my actual displacement, which represents the deformation as a function of location or x, can be found out as pi x times z naught. Okay, now phi x I have assumed as 1 minus cos pi x by 12 times 71.5 centimeters. Okay, so basically, or I mean, you can write it like 71.5 first, and this as 12 centimeters. Now, once we have that, I can find out what is the equivalent static forces as F naught x equal to, in this case, I can directly write this as gamma equivalent, okay, times mx times phi x times a. And I can substitute, remember, mx is nothing but a constant value of mass per unit length. Phi x is 1 minus pi x by 12. A is 0.112 times g, and gamma equivalent is basically 1.6. So let me write 1.6 times 1300 times 1 minus cos pi x by 12 times 0.112 times g. And if I write it in terms of kilonewton per meter, this would be 200 1 minus cos pi x by 12 times kilo, or this expression kilonewton per meter. Now the base shear could easily be calculated using the expression that we have previously derived as gamma equivalent times L equivalent times A. Now gamma equivalent I've already found out as 1.6. L equivalent I can find out from the previous classes 0.363 times the mass per unit length times L, and the acceleration is 0.112 times g, which comes out to be approximately as 0.065 mlg, which when I substitute gives me 14,500 kilonewtons. Okay, so using this example, basically this example demonstrate how to employ the generalized STOF procedure of analysis to find out the response of a continuous system using the similar methods that we have used previously for a single degree of freedom system. Okay, all right, so this gives the idea of how to analyze continuous system. Now we are going to discuss another type of a specialized system, which is basically a lumped mass system. So this is not a continuous system, however, this is a lumped mass system. Okay, and especially we are going to consider shear type building. Okay, so first I need to define what is a shear type building. Okay, now if I consider any building representation, so let me consider a 3-story building here. Okay, I have this building here. Now this building has beam and columns. Okay, and we typically assume that all the masses are actually concentrated at the floor levels. Now for this, if I consider that the axial deformation can be neglected, okay, and at the floor level, the beam is actually in combination with the slab. So I can, if I assume that the flexure deformation in the beam can be neglected, then, so the second assumption is that flexure deformation of beams are neglected. So first you try to understand what those assumptions mean. If you consider any column or any beam, okay, like this, if you apply axial force, the displacement is actually very small because the axial stiffness is very high. However, if you apply a lateral force, then you are relatively, it takes you a smaller force to actually generate some finite displacement. Okay, so in this case, we are doing the same thing. We are saying that for the shear type building, I'm not going to consider any axial deformation in the beam or column. Okay, and I'm not going to consider any flexure deformation in the beam. So if you remember, in general, okay, in general, a 2D system at any node would have 3 degrees of freedom, right? This you might remember from your structural mechanics class. Now, if I say that the axial deformation on the beam and columns are neglected, this system basically reduces to this. Remember, there are no axial deformation, so this and this can be removed because there is no vertical deformation due to column in the column. Okay, and there is no axial deformation in the beam, then deformation at this point and at this point would be same. So I can write down a single degree of freedom system to represent the horizontal deformation. I still have these two deformation, okay, which is basically the flexure deformation or the deformation along the flexure degree of freedom at these two nodes. But if I assume that the flexure deformation of the beams can be neglected, which is a reasonable assumption if you consider a fixed column of a structure in which you have slab at each floor level, so that the beams are connected to the slab and it provides us, okay, very high rigidity to the beam, then these flexure deformations can be neglected. So I have at, or this is a single story, because we had considered single story, for each story I have only 1 degree of freedom. So in this case, okay, a shear type building can be represented using the horizontal deformation in the shear direction at each level. Okay, so for example, this shear type building, okay, I would have only 3 degree of freedom to represent the horizontal deformation at 3 stories that we have considered here. Okay, now the question is, okay, we are going to learn about multi-degree of freedom system later using exact, finding out exact deflected shape and doing all sort of analysis. However, my question is there a way that which I can analyze this multi-degree of freedom system, okay, using methods of single degree of freedom system? Okay, so I'm going to employ the same method that I did for continuous system. If somehow I can predict how does this deflected shape look like, okay, then I'm going to, or I would be able to reduce this system to a single degree of freedom system with K equivalent and M equivalent, and then again I can do my job. So again, this is also an approximate method. So I'm analyzing a multi-degree of freedom system or a multi-story building using single degree of freedom system. Okay, and the precursor for this one here is that we need to assume the deflected shape. Okay, now in this case it is not called a shape, okay, it is actually called a vector. Okay, because in this case what do we do actually? Okay, in this case we represent, let us say, if I have a building initially at this position, and then let us say it is deflected like this, and the degrees of freedom are defined at these level. Okay, so somehow if I'm able to represent what is the shape represented by these degrees of freedom, then I would be able to find out my shape vector. Okay, so to do that, let us say at any degree of freedom j, I can write down my deformation coordinate, okay, ujt as pi j times zt, where j is the degree of freedom that I'm considering. Okay, so for in this case, remember when we had a cantilever beam, I had represented this deflected shape phi x as different shape functions. Okay, one of them was 1 minus cos pi x by 2l. In this case, what I'm going to do, I'm going to represent a shape vector which basically represents, let us say, if it's a straight line, I would say this is 1, okay, this is 2 by 3, this is 1 by 3. So phi, I can write it as, if this is 1 by 3, 2 by 3 and 1, something like that. And then this represents the shape, which basically says that these different coordinate, although they would vary in time, okay, however at any time instant they would always be in this proportion represented by this shape vector here. Okay, and the total deformation u at any time instance, okay, can be written as vector, so again this would be vector phi times zt, which is zt is just one value. Okay, so this is somewhat similar to what we have already done, so I'm not going to repeat the whole derivation, I'm just going to write down the final expression. Okay, I'm going to write down the final expression for the mass equivalent and the K equivalent. Okay, now remember, for shear type building, if I consider this, okay, we represent story stiffness as Kj at jth story, let us say, sum of stiffnesses of all the columns at that particular story, the jth story. Okay, and if it's a shear type building, I can simply write this one as summation 12 ei by h cube over all the columns. Okay, and we utilize this, and the story shear in that particular story can be written as Vj equal to Kj times the relative deformation. So what I'm saying, let us say at any particular story, jth story, okay, this the relative, or instead of doing this, let us just do this. Okay, again let us draw multi-degree of freedom system. So at any story, let us say the shear force in that particular story would be the story stiffness, let us say this is Kj, times the relative deformation. Okay, so if this is, let us say, j minus 1 and this is uj, okay, the drift, story drift is defined as delta j is equal to uj minus 1. So the deformation of the floor above and below, or the floors that constitute that particular story, this would be equal to del j, which is uj and uj minus 1. Okay, and remember this expression here. Okay, this in terms of element, this expression can be written as ujt is equal to pi j times zt. Okay, so like the derivation we had done for continuous system using the principle of virtual work, I can again derive the similar expression. However, in this case, what I'm going to write down just the final expression. So M equivalent comes out to be, now there is a summation term because it's a discretized system, not a continuous system. Okay, this comes out to be z equal to 1 to n. Okay, where j is basically the degree of freedom. Okay, so mj phi j square. Okay, and then similarly I can write down, okay, I can write down the expression for kj, which, or sorry, k equivalent, which comes out to be j equal to 1 to n kj phi j minus 1 whole square, and L equivalent as summation j 1 to n, okay, mj phi j. All right, so like continuous system, we can utilize this expression for a lumped mass system like a shear building to find out the response. And all I need to do is assume the deflected shape. I can assume to be a straight line, I can assume it to be parabola, but in each case I would represent the deformation at particular degree of freedom in terms of a vector. This is the only difference between a lumped mass discretized system with the continuous system. Okay, and this would become more clear when we do one example. So let us consider, okay, in this case a 5-story building, okay, in which I am assuming that at each level the mass is same. So 1, 2, 3, 4, and this one becomes 5. Okay, 1, 2, 3, 4, 5. All these masses are m actually, and all these story stiffnesses are k. Okay, and let us say we assume that it actually deflects linearly, so that if I assume that the topmost coordinate is 1, then this would be 4 by 5, this would be 3 by 5, and then 2 by 5, and then 1 by 5, so that I can write down my shape vector as 1 by 5, 2 by 5, 3 by 5, 4 by 5, and then 1, which is basically 5 by 5. Okay, so my mass equivalent would become, okay, so my mass equivalent would become nothing but mj, which is m for all the system, and then this square. So m times 1 square plus m times 1 by, or sorry, 4 by 5 square, okay, then m times 3 by 5 square, and so on up to m times 1 by 5 square. And once I substitute these values, okay, I get final mass equivalent mass is 11 m by 5. Similarly, k equivalent, okay, I can write it as k at each level times, first let me just write down that expression, because this would be j equal to 1 to 5, okay, and then this is kj times phi j and phi j minus 1 square. Okay, so this would be k 1 minus 4 by 5 square plus k 4 by 5 minus 3 by 5 square plus k 3 by 5 minus 2 by 5 square, and so on, 2 by 5 minus 1 by 5 square. Okay, we can simplify that and we see that the k that we get is actually k by 5. Okay, and similarly we can find out the L equivalent as well, okay, which is basically in this case I would get as mj times phi j equal to 1 to 5, and you can substitute the value and this would basically come out as 3m. Okay, so we have seen that by assuming the deflected shape vector, I have been able to reduce this system to a single degree of freedom system in which it can be represented as k equivalent and m equivalent, where k equivalent and m equivalent have been derived like this, and the equation of motion would become, okay, in this case z double dot plus omega n square, which I can easily find out. Okay, omega n is nothing but, in this case, k equivalent divided by m equivalent under root. So this plus z equal to minus L equivalent divided by m equivalent, okay, times UGT if there is a ground acceleration. Okay, Remember, omega n equivalent is nothing but k by 5 divided by 11 m by 5, which comes out to be 0.3 times k by m. Okay, so we have seen that we solved continuous system, and we solved lumped mass multi-degree of freedom system, a shear type building as well, without having to solve a multi-degree of freedom system. So this is the power of a generalized system, okay, by utilizing or assuming a deflected shape or a shape function or a shape vector for a discretized. Okay, in subsequent classes, we are going to see how to solve a multi-degree of freedom system without any approximations, without assuming that what is the deflected shape will look like. We would be actually able to find out what would be the deflected shape actually looks like. Okay, and we will do that in subsequent classes. Okay, all right. With that, I would like to conclude this class. Okay, thank you very much.